Good morning. Today we're going to be talking about the bilinear transformation. In the last video, we talked about how to design analog filters. And I had said that what we're going to do when we want to design a digital filter, what we're going to do is design an analog filter and then change it over to make it a digital filter. And so that transformation from an analog filter to a digital filter is what we're going to talk about today, and that's what we call the bilinear transformation. And as I write here, the bilinear transformation, we go from HA of S, our analog filter, to H of Z, which would be our digital filter. So the bilinear transformation is really a mapping. So we can think about is going from the S plane, where HA of S is, to the Z plane, where H of Z lives. Now, a couple of things. If our continuous time system is going to be causal and stable, all the poles are going to be in the open left half plane. And so all the poles of HA of S are going to be over here in the dashed section. Now, we know from our study in this class that for causal, stable, discrete systems, the poles have to be inside the unit circle. And so one thing we'd like to do is take all the poles from H of S that are in the left half plane and convert them into poles inside the unit circle, because if H of A of S is causal and stable, we want H of Z to be causal and stable too. So the transformation is this. The transformation is just substituting S for 2 over T, Z minus 1 over Z plus 1. And so H of Z, our discrete filter, is just going to be the filter we designed analog, making this substitution. Now, although we're not going to derive this substitution, we are going to show that it works very nicely. The first thing is what I just said. We want causal stable filters to translate into causal stable filters in the digital domain. The other thing we need, and though it's maybe not obvious now, if we're going to do the transformation, we need to know the specifications of the system. Now, if we're going to design a digital filter, what we have are the specifications for H of Z. Now, if we're going to design an analog filter and then transform it into H of Z, we need the specifications for the analog filter that we're going to design. Now, how do we do that? If we have the specifications for H of Z, how do we get the specifications for H of A of S? And so we can look at the bilinear transformation and see how that comes about. First of all, S can be written in rectangular form, real and imaginary part. If we take the bilinear transformation and turn it around, the bilinear transformation as it's written here is S in terms of Z. But if I solve for Z in that equation, we get this. And so if we write S as real and imaginary part, we would get this thing here. And I write it out like this just so we can find the magnitude relatively easily. So for this case, this would be Z. We're going to take the magnitude, and so we take the magnitude of the numerator and the magnitude of the denominator. The magnitude of a complex number is the real part squared plus the imaginary part squared, and then we take the square root. And we do that for the numerator, and we do that for the denominator. And we notice some things immediately. Once we look at this, we say, okay. What happens if sigma is equal to 0? In other words, what happens when the real part of S is equal to 0? Now, looking at this equation, if sigma is equal to 0, this would be 0. This and this are the same because they're squared, and so the negative goes away. And so this magnitude is going to be equal to 1. In other words, if sigma is equal to 0, the magnitude of z is equal to 1. What does that mean? Well, it means sigma equals to 0 is what? It means we're on the j omega axis. And so it means that every point on the j omega axis is going to transform into some point on the unit circle, some point when the magnitude of z is equal to 1. Now, what happens if sigma is greater than 0? Well, we look at it here. If sigma is greater than 0, it means the numerator is greater than the denominator. So the magnitude is going to be greater than 1. Right? If it's the other way around, the same thing. If sigma is less than 0, then this would be a negative number and this would be a positive number. So the denominator would be larger and the magnitude of z is less than 1. In other words, right, sigma greater than 1 means we're in the right half plane, and everything in the right half plane translates into a magnitude greater than 1. And so the whole right half plane of the z plane transforms into outside of the unit circle. When sigma is less than 0, it means we're in the left half plane, and it means that the whole left half plane transforms inside the unit circle, right, where the magnitude of z is less than 1. And so, of course, this last one tells us that if we have a pole in the left half plane, it's going to transform into a pole inside the unit circle. And so stable causal systems for h of s are going to translate into stable causal systems of h of z. And this is just written out what I just said. Now, we also need a simple way to get the specifications. Now, the way to do this is to make sigma equal to 0. Sigma equal to 0 means that s is j omega. Right? The specifications come from the frequency response. And so we set sigma equal to 0 to get the frequency response. Right, when h of s, when s is equal to j omega, is the frequency response. And we know from part 1 that if sigma is equal to 0, the magnitude of z is equal to 1. And so z would be e to the j omega, right, if we write this in polar form. And so substituting z, this is what we would get. Substitute s, we get this. Substitute z, we get this here. Now basically, this gives us a relation between the continuous frequencies and the discrete frequencies. All we have to do is simplify this equation to get our relationship a little easier. As always, we have a complex exponential and a 1, so we factor out half of the exponential both in the numerator and the denominator, so it's the same thing here. And this is what we get. Of course, these terms cancel out. This can be written as 2j sine, the denominator can be written as 2 cosine. The 2's cancel out, the j here will cancel with the j on the other side. And so we just get 2 over t and sine over cosine, which is tangent. And this is the relation between the continuous time frequencies and the discrete time frequencies when we're using the bilinear transform. Sometimes there is some confusion once in a while. We already have one relation between continuous time frequencies and discrete time frequencies, and that happened when we were sampling. Remember, there was a relationship between capital omega and little omega that had to do with f of s. That was the relationship when we're sampling. This is the relationship when we're using the bilinear transform. And the way we use this is relatively simple, right? This gives us a relationship between little omega and big omega. So in other words, let's say these are the specifications of the digital filter that we want, right? So it would be in little omega. We can use our formula to change little omega p into capital omega p, and the same thing for omega s. And so these specifications would change into these specifications for the analog filter. Notice that the magnitudes stay the same. What changes are the frequency. And this change from little omega to big omega, right, change from the specifications of h of z to the specifications of h of s is called pre-warping. It's called warping because this relationship, as we can see, is not a linear relationship. Now, the t in the bilinear transformation is a constant. It's not the t that we used in sampling, okay? It's just a constant, and it could actually be anything. Generally, to make our life easier, we either choose it in one of two ways. We make t equal to 2, and so if we make t equal to 2, well, this simplifies. Or we choose a t so that omega p is equal to 1. Let's do an example to see this with numbers. So these are our given specifications, 0.2 pi and 0.4 pi, as the pass and stop frequencies. And let's do our pre-warping both ways. Okay, so let's say we choose t to be equal to 2. This will be our relationship. We can substitute omega p in, and we can calculate whatever the tangent is, right? 0.32, 0.33 in this case. We do the same thing for omega s, and we get our frequencies. And so these would be the frequencies, or these would be the specifications that we now use to design our analog filters, what we had talked about in the last video. On the other hand, sometimes we want omega p to be equal to 1, and if that's the case, right, we substitute in here omega p equal to 1, we solve for t, and once we get t, we use it in the second equation to solve for omega s. And so these would be the solution, right, in that case. Notice that in each case, what's going on here, right? This frequency, 0.4 pi, is double 0.2 pi, right? This is double the frequency. The stop frequency is double the frequency of the pass frequency. Here, once we do the transformation, the warping, 0.72 is not double 0.32, it's more, right? The same thing is 2.2 is more than double 1. And so the relationship of the frequencies changes. That's why they call it a warping of the frequencies. I want you to do this. So given these specifications for h of z, find the specifications for h a of s. And I want you to do that for these specifications and for these specifications. Do the pre-warping.